Hello everybody, we're getting ready to do homework, or rather classwork. Yeah, this is classwork lesson 3.5 part 2 for pre-calculus math today. If you need note-taking guides or homework guides, homework sheets, email me here. 3.5 part 2 exponential logarithmic models here. You got 64 points here on your classwork sheet, and you got 6 points here for your notebook. Your notebook guide. And teachers, today's bell work. We'll divide using synthetic division here. Same thing down here using synthetic division, students. So give your students about 5-6 minutes for that. Okay, welcome back for the solutions for today's bell work. Up here, synthetic division, remember you change the sign to whatever it is, opposite of that, so it's 4, and then you set up a bar here, like almost like long division, and then you drop down your 2, multiply 2 by 8, combine 0, 4 times 0 is 0, drop down your 3, 4 times 3 is 12, combine. You have a remainder here of 3, so you have 2x squared plus 3 plus 3 over x minus 4 would be your quotient for this problem up here. And then down here, change the sign here to -5, drop down your 1, multiply -5 times 1, combine, -5, -5, 25, combine, 25, then -5 times 25, -125, combine, and then -5 times this would be 640, combine, you 641. So here would be your quotient here, would be x cubed minus 5x squared plus 25x minus 128 plus 641 over x plus 5 for the second one. Okay, into today's lesson, classwork. In living organic material, the ratio of content of radioactive carbon isotopes, carbon-14, to the content of radioactive carbon isotopes of carbon-12 is about 1 to 10 to the 12th. When organic material dies, its carbon-12 content remains fixed, whereas its radioactive carbon-14 begins to decay with a half-life of 5,700 years. To estimate the age of dead organic material, scientists use the following formula, which denotes the ratio of carbon-14 to carbon-12 at any time t in years. So to do that, you know the fixed amount here. This is your formula here for the ratio of carbon-14 to carbon-12. Carbon dating model. So this would be what you would use here. R equals 1 over 10 to the 12th, e to the negative t over 8223. And then this is what the curve looks like here, time in years. You have benchmarks here where time will yield certain amounts of carbon-14. So that's what the graph looks like for this model here of carbon dating, which is kind of cool. Okay, example 3 now, carbon dating. The ratio, let's do one. Ratio of carbon-14 to carbon-12 in a newly discovered fossil is R equals 1 over 10 to the 13. Estimate the age of the fossil. So we know that the age of this fossil will be determined by this here. So the carbon dating model, substitute the given value of R to obtain the following. So 1 over 10 to the 12e to the negative t over 8223 equals R. Here's our R here. So that's the original. And then we have this amount here of carbon-14. So we got to make this equal this, and then we solve for t. Substitute 1 over 10 to the 13 for R. So to do that, multiply each side by 10 to the 12th to get rid of our side here. So this will give us this, which we take the natural log now to get rid of this e to this amount up here. So natural log this, and then natural log that. And then now we have negative t over 8223 equals a negative 2.3026. And then when we do our manipulation here to isolate our t, meaning we multiply both sides by 8223, negative 8223, we get this amount here. So that would be our years using that amount of carbon-14. And once you find the amount of carbon-14, it's pretty simple. So to the nearest 1,000 years, you can estimate the age to be about 19,000 years for that fossil. Using graphing utility to graph the formula for the ratio of carbon-14 to carbon-12 at any time t, as this here, this will be what the graph will look like for that. And then this will be the intersection here, y equals 10 to the 12th. That's this here, and then this, I guess you just call it a line here. Where this graph intersects this line is where your time amount would be on your x-axis here. Setting up your viewing window here is a little tricky, and we can go over that. In the same viewing window graph, y2 equals 1 over 10 to the 13. So to the nearest 1,000 years, you can estimate the age of the fossil to be about 19,000 years, which would be right here. And you can go in the table and find that as well. So let's try a problem here. We have a word problem here. Carbon-14 dating assumes that the carbon dioxide on Earth today has the same radioactive content as it did centuries ago. If this is true, then the amount of carbon-14 absorbed by a tree that grew several centuries ago should be the same as the amount of carbon-14 absorbed by a tree growing today. A piece of ancient charcoal contains only 15% as much radioactive carbon as a piece of modern charcoal. How long ago was the tree burned to make the ancient charcoal, given that the half-life of carbon-14 is 5,700 years? So how would we solve that problem? And then this is your blank that's on your class worksheet. Let's go over it now to solve this one. So here is our situation here. Y equals CE to the KT. That is our common form here of a exponential. And we're looking for the half-life, or rather the half time it would take for this amount of carbon to be around. So 1/2 equals e to the 5,700 k. Then we take the natural log of both sides. Natural log 1/2 equals 5,700 k. And then we end up with this. K equals natural log 1/2 over 5,700. So the ancient charcoal has 15% as much radioactive carbon as it did originally. That's given. So now we plug in 0.15 C equals CE to the natural log 1/2 over 5,700 T. So we want to solve for T here. So the first idea here is to 0.15 equals E. We're going to divide out C from both sides. Then we're going to take the natural log of both sides here. And natural log 0.15 equals natural log 1/2 times 5,700 T. And then natural log 0.15 T, we're going to solve for T now, over this amount here. And then when you crunch those numbers, you come up with 15,600.7 equals T. So it'd be about that amount of time using that carbon-14 model for this problem. So Gaussian models, as mentioned at the beginning of this section, Gaussian models are the form of y equals e to the negative of x minus b squared over c. This type of model is commonly used in probability and statistics to represent populations that are normally distributed. For standard normal distributions, the model takes the form of like this here. And this would be your Gaussian model here. Used a lot in statistics. So we will try one. A graph of a Gaussian model is called a bell-shaped curve. Try graphing the normal distribution curve with a graphing calculator. Can you see why it's called a bell-shaped curve? So the average value for a population can be found from the bell-shaped curve by observing where the maximum y value of the function occurs. The x value corresponding to the maximum y of the function represents the average value of the independent variable, in this case x. So let's get into a problem like this. SAT scores, 2009 Scholastic Aptitude Test, mathematics scores for college-bound seniors roughly follow the normal distribution, and by using our Gaussian model and plugging in values here for 0.0034e to the negative x minus 515 squared over 26,912, and then here are your scores here for x between 200 and 800. So we have this function here. This is the function that will show the normal distribution graph of SAT scores, where x is the SAT score for mathematics. Use a graphing utility to graph this function and estimate the average SAT score. So the graph of the function is this bell-shaped curve. Here is the graph of this function here. This is what it will look like. The maximum value of the curve represents the average score, which should be right here. Using the max feature of the graphing calculator, you can see that the average math score for college-bound seniors was about 515. So this shows your values down here. Y equals 0.0034, and then your x would be 515 here. Let's try one now. IQ scores for adults roughly follow the normal distribution. Y equals 0.0266e to the negative of x minus 100 squared over 450. And x can be set between 700 and 115, where x is the IQ score. Use a graphing utility to graph the function. Use the graph to estimate the average IQ score. So to do this, here would be the graph here for the IQ scores for adults. And so using that graph, maximum point is x equals 100. Our right here was 115, and this will be your max here. Maximum point is x equals 100. The average IQ score is 100. Note that 50% of the seniors who took the test received scores lower than 515. So going back to the SAT, you can see here, this is the curve here. So half of the scores were below 515. I mean, you get down here to different percentages here. 50% of the population who took an SAT math, and then the other 50% were up here. Logistic growth models. Some populations initially have rapid growth followed by declining growth, as indicated by this graph here. So you have this situation, it's kind of like an S curve here, a logistic growth model, decreasing rate of growth. Once it reaches this inflection point here, it starts to flatten out. The curve flattens here, and then increasing rate of growth is especially on this bottom part here. One model for this type of growth pattern is a logistic curve given by the function, and this is the logistic curve function here, where y is the population size and x is the time. So here would be your population size, x would be the time. An example is a bacteria culture that is initially allowed to grow under ideal conditions and then under less favorable conditions that inhibit growth. A logistic growth curve is also called a sigmoidal curve. This goes in your notebook, students, so make sure this goes in your notebook. Slide 14. So let's try one now. Spread of a virus on a college campus, 5,000 students. One student returns from vacation with a contagious flu virus. The spread of the virus is modeled by this function here. Time is greater than or equal to 0. Where y is the total number of students infected after t days. The college will cancel classes when 40% or more of the students are infected. So 40% of this amount here, 40% of 5,000. So how many students are infected after 5 days? So we have the function here. So we plug in 5 here for t. And then 5,000 here over 1 plus 4999e to the negative 4. Negative 0.8 times 5 is negative 4. And then when you crank this out, you get 54. So for 5 days, you have 54 students who are infected. Here is the curve here that follows the logistic growth curve shape. Here, this is a minimum down here, x equals 5, y equals 54. So from day 5, we know that much from the curve. So use the value feature to estimate that y equals 54 when x equals 5. So after 5 days, about 54 students will be infected after 5 days. So a conservation organization, let's go into a guide practice, releases 100 animals of endangered species into a game preserve. The organization believes that the preserve has a carrying capacity of 1,000 animals and that the growth of the herd will follow the logistic curve here, provided here, where t is measured in months. What is the population after 5 months? Well, we plug in 5 here on our function. We crank this out here, and we get 203 animals after being provided with this cool little function here for that. After how many months will the population reach 500? So for that, 500 equals our function here. We're going to solve for t now. So 1 plus 9e to the negative 0.1656t equals 2. So the way we got this, we put this over here, then we move this over here under 1,000. And then we move our 1 over here. And then we have this e to the negative 0.1656t equals 1 over 9. So we move our 9 over here. And then we take the natural log of both sides and we isolate our t. And when you crank this out, you'll get 13 months for the population to reach 500. You could graph this too, probably, and find that as well, the original function. Use the graphing utility, graph function. Use the graph to determine values of p. So this is what your graph should look like, graphing that function at which the horizontal asymptotes occur. Identify the asymptote that is most relevant in the context of the problem and interprets its meaning. So the horizontal asymptotes are p equals 0 and p equals 1,000, which, well, I guess would be about right here, as time increases. So that'd be how you do that. And that is 3.5 part 2. If you need any materials, email me here. Tutoring, whatever, email me here. Thank you very much.